Hello everybody. Let's do a deep dive into functions. This is section 1.4 in the pre-calc book. You may have heard functions defined as a one-to-one relation from one set to another set. That's sort of the technical definition of a function, put kind of simply. But what does that mean? So let's see an example here. Let's say we've got one set of data, time of day, and compare it to another set of data, the temperature. A one-to-one relation means is that every item in this time of day is mapped to only a single item into the other data set. So for example, at 1 o'clock p.m., maybe it is 10 degrees Celsius. And then it starts to warm up a little bit, and at 2 o'clock p.m., it's 11 degrees Celsius. So there's mapping nice and cleanly from 1 to 1. But if I said, well, at 2 o'clock, it is also 13 degrees Celsius. Well, this too can't be mapped to two different things. It's either 11 degrees or 13 degrees. It can't be both at the same time at 2 o'clock, so that would not be a function. There's an example. 2 is mapping to 11. My input of 2 o'clock has two separate outputs. That's no good. That would not be a function, so we can't have that. But at 3 o'clock, it could still be 11 degrees Celsius. That's fine. 2 o'clock it's 11, and my input is 3 o'clock, my output is 11. And then maybe at 4 o'clock it starts to cool off and we drop down to 10 degrees. And then by 5 o'clock it's 8 degrees Celsius. The day is cooling off as it goes. Now, everything here, it doesn't have to be mapped to every single number in the temperature range. Looking at this, I would just ignore those numbers there. Now, there are other ways to test for functions. For example, here's a couple graphs, so we could test it graphically. Here's a temperature time, 1 o'clock, 2 o'clock to 6 o'clock, and temperature 5 degrees, 10, 15, 20 degrees. And you can see here that graphically this is at 1 o'clock and it's about 12 degrees. About 8 degrees. Then at 2 o'clock it's about 12 degrees. At 3 o'clock we're up here 13 degrees. At 4 o'clock it's back down to 10 degrees, and then it's dropping back down again. And at 3 o'clock, well, let's say at 4 o'clock here, where it's 10 degrees, it cannot be 4 o'clock 10 degrees and also 15 degrees. Now, graphically, to determine that this, now that I've put this other point here, to say, oh, that's not a function that way, I would use something called the vertical line test. And the vertical line test is just as it says. It's a vertical line, and I'm going to get a vertical line here. Let me just get it from this paper clip. There we go. If your vertical line hits more than 1 point, here's a vertical line, 1 point, 1 point. Right here it's hitting 2 points, not a function. Let's get rid of this, because that's not really what I had. My vertical line going through my function only hits 1 point at a time, so this is fine. It's a function. It passes my vertical line test. Does my vertical line hit more than 1 point? No. Don't even need the dots. Look at this graph here. Boom. My vertical line is hitting 2. This graph here is not a function. It's still a graph of some equation, but it is not a function. And yes, I do see that I spelled graphically wrong. Thank you very much. Can't believe I did that. Okay. Another way to test for function is algebraically. Here's a couple of functions. I'm going to solve for y as a function of x. Basically, like we've been doing for a long time, we're going to get y all by itself. So for this one, I'll simply say subtract x squared from both sides to get y equals negative x squared plus 1. And this is going to be a function. Yes, if I input a number for x, I'm only going to get one answer out every single time. I will get a single answer out. If I put in a number, I got a unique output. Whereas for this one, when I solve for y squared, let's see, y squared equals x plus 1. And then I'm going to take the square root of both sides. So y equals plus or minus x plus 1. And there. That's shown me two outputs, a positive and a negative. That's not a function. So we're going through these functions rather quickly. We're just touching various bases on them. This is sort of introductory level stuff for pre-calculus honors. So let's take a look at another type of function, piecewise defined function. There's all kinds of functions here. Here's a piecewise defined function. And this can be a little tough to grasp at first, but we've got f of x equals, well, it equals x squared plus 1 when my input x is less than 0, and x minus 1 when my input of x is greater than or equal to 0. So this is a function. Even though it looks a little advanced, I've got two different options here for different types of inputs. Let's see what that means. So let's say I want to solve for f of negative 2. Well, I look at f of negative 2. My x value is less than 0, so I'm going to use this top one, x squared plus 1. So f of negative 2 is going to equal negative 2 squared plus 1. Negative 2 squared is 4, 4 plus, so it's 5. How about when f of 0? Well, I'm not going to use this top one because I only use this top one when x is less than 0. When x is greater than or equal to 0, I use this bottom one. So f of 0 is going to be 0 minus 1 or negative 1. And f of 2, well, same thing. I'm not using this top one. That's only when my x value is for less than 0. When my x value is greater than or equal to 0, I'll use this bottom one, x minus 2. You can have like 5 here, 3, 4, 5, as many pieces as you want. This is only broken into 2 pieces. So f of 2 is going to equal 2 minus 1, so it equals 1. So that's how you solve for the input and the output for a piecewise defined. But how would you graph something like that? If I wanted to graph this, well, let's see. I already got some points. When x is negative 2, when my input is negative 2, my output is 5. So when x is negative 2, f of x is 5. 1, 2, 2, 4, right there. 5. That's going to be on my graph. When x is 0, y is negative 1. That is on my graph. And when x is 2, f of x, or my output y, is 1. All right. But I don't just connect those points. There's lots and lots of points I can do. Here's how it works. If I've got 2 pieces, I'm going to graph both pieces. X squared plus 1. That is a parabola because it's squared and it's shifted up 1 unit. So my parabola starts here and it would look like that. Okay? I know that's faint. That's faint on purpose. And the other one is x minus 1. So that's just a straight line, right? It's a linear equation with a y-intercept of negative 1. So there's negative 1, and it's going to look like that. But as that stands, this does not pass my vertical line test. And I said this is a piecewise defined function. It's a function, f of x. It says it right there. F of x, it's a function. And it's not passing it. Well, that's because I have to take the domain in mind. I only want the x squared plus 1 where x is less than 0. So here's 0. I'm going to put an open circle right there and only darken that side. So as my domain goes from negative infinity to negative 5, negative 2, negative 1, 0, it's coming here. But once it gets to 0, it jumps and becomes a straight line here. And it includes that point. So that darker part, that is my function. I'm going to erase these other parts. Those aren't in my function. That's what the graph of this piecewise defined. Two pieces, or rather a quadratic piece coming in here, and now it passes my vertical line test. Even here it passes my vertical line test. It's touching that point, but that open circle means that it's not including that point. So it only hits one point there, and then still. That is a piecewise defined function, both algebraically and graph. Okay, next on our agenda, we're going to look at two different functions, and we want to find all the values for which the functions of one, f of x, is the same as g of x. So where those two functions are equal to each other. Where does f of x equal g of x? Well, here's f of x, x squared plus 1, and g of x, 3x minus x squared. So let us solve this by setting f of x equal to g of x. And we'll solve this, let's see, by factoring. First thing I want to do is get everything to one side and have it set equal to 0. So let's add x squared to both sides and subtract 3x from both sides to leave us 2x squared minus 3x plus 1 equals 0. All right, so this is how you solve a quadratic. We're finding the roots. We set it equal to 0. Now I'm going to factor this. Let's see. Equals 0. So to get that first term, we're going to have to be 2x times x. To get 1, it's got to be 1 and 1. Those are the only thing. And both sides are the same because of their positive, and they're both negative. So that's going to be minus, minus. There, that's factoring. If you have trouble factoring that, you may need to review it. Something like that, because that was pretty easy to factor, I think. First times the first, first, and then outer, inner, and then the last, negative 1 times negative 1, that gives you positive 1. And negative there. All right, set each equal to 0. So 2x minus 1 equals 0, and x minus 1 equals 0. So x is 1/2, and x equals 1. There. Those are the values where they are equal. But I want to show you something kind of neat here. I have a favorite app. It is called Desmos. This is it here. It's available for all tablets. There's also an online version that's really good, a web-based version that we'll use in class as well. So let's open up that Desmos. And what do I want to do? I've got two functions here. I'm going to graph them both so I could find it graphically just using this quick little app. X squared plus 1. There. Bit of a glare on that. Huh? Let's see if I can cut that out a little bit. I don't know, maybe. X squared plus 1. I'll zoom in. There's one of them, and enter, and use my other app. We've got, it's not showing up. I'll bring it up here, close. So there's x squared plus 1, and the other one was 3x minus x squared. 3x minus x squared. And now look at those graphs. You see where they're touching? That's where they're equal. I'll zoom in. And they are touching here, and right just a touch screen. Boom. They are equal when x is 1. When x is 1, the output for both of them is 2, and they are also equal when x is 1/2. When you input 1/2 for both, you get, well, 1.25 is showing up a little bit there. So what I found algebraically here, by setting them equal to each other, you could use a graphing calculator, but I'll tell you, there's nothing easier than this Desmos. It just types right in. I know that's kind of fuzzy there. And you can see exactly where it is crossing. Pretty neat, I think. Okay, let's just write a couple functions here to help us wrap our heads around it. Here's a cylinder, and in this cylinder, the height is 4 times greater than the radius of this cylinder, right? H over R is 4, but if I multiplied both sides by R, then, the height will equal 4 times the radius. And I want to write the volume of this cylinder as a function of the radius. Well, I know, and perhaps you do too, that the volume of a cylinder equals pi r squared times the height, right? Pi r squared would be just for the circle, and then multiply it by the height, and you get the whole volume. So if I want the volume as a function of the radius, well, what I want is V of R. And V of R, well, that will equal volume as a function of radius. And if you see this, like f of x, that's a function of x. This is volume as a function of r, V of R, right? Volume of radius, V of R. Same thing, pi r squared h. And, well, since I only want the radius here, I'm going to replace this h, because I only want it as a function of the radius. So that's going to equal, playing with colors here, pi r squared, and that h, I'm going to replace it with 4r. So the volume as a function of the radius is, let's see, r times squared times r, so 4 pi r cubed. Volume as a function of the radius means I only want the radius in my function. I don't want any height. In this other one here, volume as a function of the height, I'm going to do the same thing, but and get rid of the radius term. I only want it in terms of the height. So the volume as a function of the height equals, well, pi r squared h. But let's see, this r squared, I want it gone. So let's see, I want the r gone. So let me solve this for r. R is going to equal h over 4. Because I want it only in terms of height. So that equals pi times h over 4 squared times h. That equals pi h squared over 16 times h. And just to put a little more cleanly, that's going to equal h squared times h. H cubed over 16 times pi. Or I could have put pi in the numerator up there. that's fine as well. Matter of fact, I think I will. Pi h cubed over 16. That is the volume as a function of the height only. Okay, we're going to end the section with something a little advanced, I guess, and that's the difference quotient. And this is something you see the first week of calculus class, the difference quotient. Because, and this is it here, f of x equals f of x plus h minus f of x divided by h. What is h, you ask? I'll tell you in a second. But what this difference quotient does, let's say we had a quadratic like that, something like this, which was, be x squared to make the parabola like that. And I have a single point here on it. And I draw a tangent line through that point. A tangent line would touch this graph only at this point. If I, make this line any other way, like that, it's going to hit it at 2 points. The tangent line, I only want to hit at 1 point. This tangent line has a slope. The difference quotient gives the slope of the line at this point. And let's say you had another point here. Difference quotient would give us a negative answer for that one because it's given a slope and it's negative. So it can be a little tough to wrap your head around at first. So let's not worry too much about it. Let's just play with it algebraically, all right? So let's use it. Oh, h, by the way. The distance from this point to this point, all right, we're going to call that distance h. And as this point slides along the graph to here, you can see that h distance from one point to the next getting smaller and smaller until it gets to pretty much 1 point here, and it gets to be, the distance between gets to be practically 0, but not 0. Because if it was 0, I couldn't divide by it. So h is just going to be a number that is just infinitesimally small, but not 0. But awful close to it. So let's play around with this a little bit. Let's say I've got f of x is 2x plus 4, and I want to find f of x plus h minus f of x over h. Well, a nice way to do it is to first find out what is f of x plus h. Well, since f of x is 2x plus 4, I mean f of 2, that would equal 2, and out goes the x, and in goes 2 in its place, plus 4. 4 plus 4, that would be 8. What if I wanted f of negative 10? Well, that would equal 2, and the x is just a placeholder, so negative 10 goes in, and then plus 4. What if I wanted f of a smiley face? That's a pretty lousy smiley face. Well, then I'd do 2 times that smiley face plus 4. This is just a placeholder. So if I wanted f of x plus h, well, all I have to do is 2 times, not 2, not negative 10, not smiley face, but x plus h. And still plus 4. All right, we'll distribute the 2, and that is 2x plus 2h plus 4. That's what f of x plus h is. So f of x plus h, 2x plus 2h plus 4 minus, I already know what f of x is. It was given to me. F of x is 2x plus 4. So I'm going to subtract from that 2x plus 4, that whole thing. maybe parentheses isn't a bad idea for this first guy too while we're still playing with it. And that is all over h. Well, let's simplify this numerator. 2x minus 2x, 0. 2h minus nothing. Well, I still have 2h. And 4 minus 4, well, that's going to be 0. And the over h, those cancel out. The h over h cancels out. And my answer is 2. Not a surprise, since I said that the difference quotient gives you a slope. Look at 2x plus 4. 2 is the slope. But that's just for a line. It's a constant slope. This, depending on where the line is, the tangent line could be anywhere floating around. It just all depends on what point you want to pick, right? If I want a line that's tangent to this point, well, that's going to look like it's going to have a different slope, right? Not going to get the same answer every single time. So let's take a look at one that's a little more advanced. F of x is x squared minus 4x plus 7, and I want to use the quotient, the difference quotient for it. Well, let's start in the usual place by finding just what is f of x plus h. F of x plus h equals, wherever I see the x, I'll put x plus h squared minus 4 times x plus h plus 7. So this might get a little messy here to start. X plus h squared, well, let's see, that equals x squared plus 2hx plus h squared, right? I just did FOIL, x plus h times x plus h. This is what I get. And let's see, negative 4 times x minus 4x, negative 4 times h minus 4h, and I still have the plus 7. I don't really see anything. Oh, that should be 4h, shouldn't it? Minus 4h. Looking for like terms, all I really have is, well, nothing, right? That's 2hx, x squared, h squared, 4x, not squared. I don't have any like terms. So that's what f of x plus h is, this, no like terms. Let's write it out. X squared plus 2hx plus h squared minus 4x minus 4h plus 7. Phew. Minus. And what is f of x? I've already given that. X squared minus 4x plus 7. And this is all over h. Let's simplify this numerator, okay? How do I do that? Okay, let's do it this way. I'm going to drop the parentheses. No signs are going to change in this first one, right? I've got x squared plus 2hx plus h squared minus 4x minus 4h plus 7 minus everything in here. So this negative has to get distributed. So that's minus x squared plus 4x minus 7 all over h. Let's simplify this numerator now. I've got x squared minus x squared. That's gone. Negative 4x plus 4x. That's gone. 7 minus 7. That's gone. So all I'm left up top is, let's see, 2h plus h squared, no, 2hx minus plus h squared minus 4h divided by h. Let's clean it up a little bit. How about if I factor out h? H outside of 2x plus h minus 4. Those can cancel, those h's, and my final answer, this equation, put through the difference quotient, run through that ringer of the difference quotient, my final answer is 2x minus 4 plus h. And I'm leaving the h there, even though it's often in calculus, you get rid of it because it's just a number that's so small. It might as well be 0. It's so infinitesimal. That's the answer, 2x minus 4. Thanks for listening.